Okay, so design of members for flexure. So basically, yung members na subjected to flexure or bending are beams. So kapag yung member is subjected to axial compression, that those members are columns. Kapag yung members is subjected for flexure or bending alone, they are your beams. So for this discussion, I will be discussing beams. Okay, so yung axial compression natin, medyo shorter yung solution nun compared sa bending. Medyo mas mahaba yung i-consider natin. Okay, so before we start, here's some definition of beams. So beams are horizontal members seen in a structure spanning columns. So they support loads which are resisted by bending and shear. So ang i-discuss ko is both pag-consider ng bending and ng shear. It also supports floors, roof sheeting as purlins, and side cladding. Okay, so these are the types of purlins. So we have floor beams or major beam supporting secondary beam or joist. Next is a girder beam or a floor beam or a beam supporting another beam. So minsan, di ba, may makikita tayong girder? So they support another beam. So sila yung mas mga malalaking type of beam. Next is your lintel beam or used to carry wall load over openings or example doors, windows. So sa mga openings kasi, di ba, most of the time yung walls natin is made of CHB. Now, we put lintel beams dun sa gap para sila yung mag-carry ng load ng mga CHB. Since hindi naman siya pwedeng i-carry directly nung frame ng door kasi sisira siya o middle. So, yun yung tinatawag nating lintel beam. Doon na siya ginagawa mismo after nyong mabutas yung or magawa yung opening for doors and windows. So, maliliit lang siyang beam and hindi din siya pansin since kapantay lang siya ng wall. Next, we have your purlin. So, yung purlin pala sa roof is a type of beam. So, they are a roof beam supported by your roof trusses. So, I hope you know what a purlin is, no? Diba? Sa truss natin, meron tayong C purlin, most of the time C. Meron tayong CL. So, there are different types of purlin. So, ang analysis ng purlin is sa flexure din. Next, we have your rafter or roof beam supported by purlins. Ano ba yung rafter? Sige, dun sa hindi alam, no? Di ba ang trusses natin? Kung, di ba ganito? Di ba ganyan? Ang familiar kayo yung parang Warren truss o yung mga ganitong klaseng truss. Yan. Now, yung rafter truss is, ang truss natin is, ito mismong part na to. Yan. Normally, mga ano yan, C-channel, ganyan. And then, open space sa loob ng bahay. So, yung mga ganitong klase ng truss, o most common yung mga C-channel, sila yung tinatawag natin na rafter. Kasi yung mga ganitong klaseng truss, yung may mga members, ang analysis niyan most of the time is similar with your columns. Ito naman kapag ganito yung truss natin or made up of rafters, ang analysis niya is sa beam. Ulitin ko, no, yung mga ganitong klase, yung open space para yung mga high ceiling na bahay, yung walang ganito. Ito mismo yung truss nila. This is your rafter truss. Ang purlins naman, sila yung nasa top ng truss. Para kunyari si purlin, sorry, baliktad. C purlins, no? Yan. Yung nasa top, then after nung C purlins mo, yun na yung GI sheet or any type of yung roofing na mismo ng bahay. Yan, para malinaw lang, no? So next is spandrel beam or beam at outermost wall of buildings which carry part of the floor load and exterior walls. So meron akong image na papakita later. Next is stringer beam, longitudinal beam used in bridge floors and supported by floor beams. So yung stringer beam naman, most commonly gamit siya sa mga bridges. So here are images para mag-visualize nyo, no? So again, these are different types of beams. So check natin. Ayan, ito, yung rafter, tulad nung sabi ko, no, straight lang siya. This is a rafter. Ang purlin is yung nasa ibabaw nung truss member or yung rafter. Next, ito yung spandrel beam na tinatawag. And then, ito regular beam na nagsusupport ng slab. Ito naman yung floor joist na tinatawag. Floor joist is parang may mga small intervals siya and kinikerry niya yung flooring. So, para siyang, kung ito-drawing natin, siguro, ito, mga small intervals, ganyan. Tapos, may spacing lang na, tapos another na naman. Tapos, nagkikerry siya ng slab sa top. So, small intervals ng ganito. Tawag sa kanila is floor joist. So, another type of beam siya. Nagkikerry, most commonly, ang kinikerry nila is slab or yung floor. Yeah. So, ito naman, alam nyo na to, spread footing, no, sa JEO. May JEO ba kayo? Then, wall footing. JEO and RCD yan. Okay, so ito naman yung stringer, no, commonly sa mga bridges. Ayan. So, again, type lang yun ng beams. Ang analysis nila is almost similar lang naman. So, commonly used type of beam sections. First is the universal beam or rolled section. This material is concentrated in the flanges and very efficient in an uniaxial bending. So, typical sections nito is yung I-beam. Next is compound beam. Yung universal beam, eto, kapag dinagdagan natin ng plates or flange plates, it will now be called your compound beam. So, example, meron tayong I-beam. Ito yung universal beam, yung wide flange beam na tinatawag. Yung mga W section, di ba? W250 by etc. Kunyari, ito yon. Universal beam siya. And then, kapag dagdagan natin siya ng plate sa flange, ang flange po is itong part na to. Ang web is yung nasa gitna. So, kapag dagdagan nyo siya ng plate sa flange, ganyan, for example, ang purpose niyan is to resist bending in vertical and horizontal direction. So, kapag dagdagan natin siya, it will now be called your compound beam. Yan. So, universal. Then, pag may added plates, will be your compound. Next is your composite beam. Kapag composite naman is, yung steel structure natin is may kahalo ng concrete. Now, how does that happen? For example, yung beam ng structure mo is steel. Tapos, ang sinusupport nung beam na steel is flooring na concrete. So, kumbaga, nakafix na yung beam tapos isasama siya sa buhos ng concrete. So, parang combined na siya nung steel tapos may portion na nabuhusan ng concrete. So, that is a composite beam. Then the concrete floor provides necessary lateral support to the compression flanges to prevent lateral buckling. So, composite beam. And then we have castellated beam. So these are made by applying a special technique to the wide flange I-beam. So this technique consists of making a cut in the web, magka-cut sa web of a wide flange beam in a corrugated pattern. So yung castellated beam naman, more on aesthetics to. Yung strength niya is hindi masyado. So ganito yung itsura niya. So hindi naman to important sa atin yung castellated beam. Ganito siya. So, meron siyang mga butas sa web part. So, more on aesthetics lang siya. Hindi naman siya relevant sa CE. So, here are the classification of beam sections. So, first is the bending stress of a beam depends on how well the section performs in bending. Then, the thin projecting flange of an I-beam or W section is likely to buckle prematurely. So kung thin yung flange, yung top and bottom flange, it is highly likely to buckle prematurely. So the web of an I section, yung part dito, no, can buckle under compressive stress due to bending and shear. Now, in order to prevent such local buckling, it is necessary to limit the outstand thickness ratio of flange and depth thickness ratio or the web. So, yung ratio ng flange saka nung depth mismo ng entire section, you need to consider that. And next is, when the design is made using elastic analysis, the member should be able to reach the yield stress under compression without buckling. So, dapat, ang yield stress natin is yung Fy, di ba? Yun yung portion sa curve, di ba? Yung hindi pa nagkakaroon ng permanent deformation. So, dapat ma-reach niya yung Fy bago siya mag-buckle para maging safe yung structure natin. Ito yung mga possible beam? Possible failures. Sorry. This is possible beam failures. So, yun. Yun. So, first, we have your bending failure. Kung mapapansin nyo, yung failure niya is nandito sa may center. Then, we have your lateral torsional buckling. Ang failure is yung nasa web part. Then, shear failure, andito sa may support. Then, bearing failure or web crippling, if mananotice nyo, dito tayo sa cross-section, nagkaroon ng deformation yung web part ng I section. And then, we have your excessive deflection. So, magkakaroon ka ng failure dito sa lower portion of your beam. So, most of the time, it is common na kapag mag-design tayo ng beam, we need to consider all this for us to make sure that your beam will stay safe. So, pag nag-design, dapat okay siya sa bending, dapat okay siya sa lateral torsional buckling, okay siya sa shear, okay siya sa bearing, and then sa deflection. So, lahat ito dapat sine-check kapag nagdi-design. Now, yung sa mga common problems naman na binibigay, hindi naman yan lahat-lahat binibigay. So, kunyari, what is the allowable bending stress? So, paisa-isa lang siya, but it is important that you know how to solve for this para safe yung structure natin. Since yan naman yung ginagawa natin, di ba? Mag-design ng structures. Ayan, ito example, ganito yung itsura kapag nag-buckle yung beam. So, kung mapapansin nyo, nagkaroon ng deformation. Yun. So, we have two categories for your beam. We have what we call your laterally supported beam and laterally unsupported beam. So, for laterally supported beam, a beam may be assumed to be adequately supported at the supports, provided that the compression flanges has a full lateral restraint and nominal torsional restraint at supports, supplied by web plates, partial depth of plates, etc. So, ibig sabihin lang is may full support siya dun sa end nung length ng member ng beam. So, mathematically, maki-figure out natin kung laterally supported ba siya or not using these two equations. So, ito yung magiging basis natin. We have what we call your LC and LU. So, kung hindi naka-state sa problem, kasi may problems kasing nakalagay na the beam is laterally supported, etc., etc. So, alam na natin na nakakategorize siya as a laterally supported beam. But there are times na wala siyang qualification. So, we need to consider these two para malaman natin kung laterally supported ba siya or not. So, ito, LC is the minimum of these two equation. LU is the maximum. Pero pinaka-common naman, I think, hindi naman nagbabago. Ang LC dyan is ito kasi ito yung mas maliit din sa dalawa. And ang LU natin is ito. Now, BF, ulitin ko, that is the width of the flange. Ang FY is your yield stress. Most of the time, this is given and this varies depending on the type of steel. Pinaka-common is 836 steel, so 248 MPa. And then, ito naman, ang AF, please take note of this AF because common mistake ng students is hindi napapansin. Ang nilalagay nila is area. Since ang naka-indicate dito is AF, this should be the area of the flange. Hindi area ng entire section. So, area ng flange lang. Divided by the depth of the entire section multiplied by the yield stress. So, ulitin ko na please be mindful of the area na gagamitin dito. Kasi minsan, di ba, binibigay sa problem yung area ng section, tapos yun na yung ginagamit. So, mali ka na. So, please double check lagi. So, yan. These two yung magiging basis natin. Yan o, area of the compression flange. So, isang part lang, yung sa taas. Yan. So, case 1, we have your laterally supported beams. That is if your L or the length of the beam is less than your LC. Ang LC natin is ito. So, kapag yung length ng beam mo is less than LC, we can say that the beam is laterally supported. Now, for laterally supported beam, we have 3 categories. We have compact, semi-compact, and non-compact. So, for compact section, ito daw yung gagamitin natin na equation from nscp. First, FB or the allowable bending is equal to 0.66 Fy, bending about the strong axis. Please take note, strong axis is the x-axis, weak axis is the y-axis. So yun, 0.75 naman kapag weak axis. So ano yung condition? First condition is if your BF over 2TF multiplied by square root of Fy is less than or equal to 170. And then, if your D over TW multiplied by your square root of Fy is less than or equal to 1680, then your section is compact. So, we will use this allowable bending stress. Para saan yung allowable bending? Since mag-design tayo, we need to know kung ano ba yung allowable bending na kayang i-carry nung beam. Diba? Since mag-design tayo, kailangan natin allowable stress. Ito lang yung stress na dapat i-carry nung, ito lang yung stress na dapat nandun sa beam. So, kaya natin kino-consider dapat kung ano yung allowable bending sa beam. Diba? So, ito yung equations for compact section. Now, yung semi-compact naman is, take note here, no, less than siya. Sa semi-compact, kapag greater than na yung BF over 2TF square root of Fy mo sa 170, but less than siya sa 250. And then yung condition 2 is the same lang. So 1680. Dapat less than 1680. So may instances na mas malaki to sa 170 pero nasatisfy niya yung condition 2. It may fall under semi-compact section. So okay lang yun. Now kapag semi-compact siya, we will use this equation. Medyo mas mahaba. Yung D over TW, no, D is the depth of the section, TW is the thickness of the web. So meron naman siya mga subscript that will indicate kung ang tinutukoy ba is sa flange or sa web ng section. Wag lang ma-confuse. Kung ito yung I section natin, di ba? Web po is, ito yung web natin. Ito yung web. Ang web natin yan, ito yung web. Yan. Ito naman yung flange. So, wag nyo lang ma-interchange. Mali talaga kayo. Yan. Then, so, ito yung equation kapag semi-compact. Again, ang hinahanap natin is allowable bending stress. Yung bending stress na kaya ng beam. Next naman, of course, semi-compact. Lastly is your non-compact section. Sorry, di ko na ito na-change na. So, non-compact section is if hindi na-satisfy lahat ng to, example, yung BF2TF square root of Fy nyo is greater than 250. So, non-compact siya. Ang gagamitin nyo lang, FB is equal to 0.6 Fy sa both your X and Y axis. So, ito yung laterally supported beams. Yan. So, example. Ayan. So, compute the resisting moment of a W310 by 97. Again, yung W, that indicates a wide flange section or I-beam. Bakit siya wide flange? Kasi wide yung flange niya. Most of the time, yung wide flange section, yung flange width mo, konti lang yung difference niya sa depth. So, ito example, kung mapansin nyo, yung flange width mo is 305, yung depth mo is 308. So, kung papansin nyo, super minimal yung difference. So, kaya siya tinawag na W, void flange section. Assume the section has a full lateral support for its compression flange. So, check natin. So, since sinabi na dito na full lateral support daw, so this is under your laterally supported section. We don't need to compute your LC and LU. Yeah, so solve natin. Okay, so let's solve the problem. Copy ko muna itong section properties. Sige, wag na tingnan na lang natin. So first, diba, ang equation natin is, consider natin is BF over 2TF should times FY should be less than 170. So check natin. Ayan. BF, ang BF niya dito is 305. So we have 305 divided by 2TF, 2 times, ang TF mo is 15.4, multiplied by, square root of FY. Ang FY nung A is 248. 248. 248. Check natin yung sagot. So, 155,946. So, that less than siya sa 170. So, pwede na natin masabi na compact. So, try muna natin yung second equation. That is dTW. Check ulit natin para sure. dTW times square root of FY should be less than 1680. Balik tayo dito. So, ang depth is 308. All over TW, that is 9.91 multiplied by square root of FY ulit, which is 248. So, less than din siya sa 1680. So, we can say that the section is compact. No? Compact yung section. Wait, lumalabas kasi ito. So, the section is compact. Diba, kapag the section is compact, we can use FB is equal to 0.66 FY. Check natin, baka mali ako. Yan. So, if the section is compact, since na-satisfy niya itong dalawa, we can say that FB is 0.66 FY. So, lagay natin 0.66 multiplied by 248. So, ito yung value ng bending stress natin, 163.38 megapascal. Tingnan natin, ito ba yung hinahanap? Compute the resisting moment. So, ang tinatanong is moment. Ano ba formula ng moment? Bending stress is equal to MC over I or M over SX. Input. Wait lang. Ito na, natapos naman tayo. Input. So, so this is, the section is compact. Compact, no? Kaya ang ginamit natin, FB is equal to 0.66 FY. So, ang pag-compute ng FB, so FB is equal to MC over I. Equation, sorry. So, ang bending stress, ito general equation to, kahit saan nyo to gamitin. Ang formula ng bending stress is equal to MC over I. Now, since ang given sa problem is, check natin, may I bang binigay? Ang given sa problem, binigay naman yung I, pero meron tayong S. Mas magandang gamitin yung S, kasi pwede din kasi itong FB. FB is also equal to M over SX. So, ito na lang para mas madali. So, to compute for your M, so, from this formula or equation, pwede natin sabihin na moment is equal to FB times SX. So, to get your moment, since yun yung tinatanong, tama ba? Moment, tama. Compute the resisting moment. So, yung moment capacity nung section ng tinatanong. So, to do that, all we need to do is multiply the allowable bending, which is 163.68, to your SX or your section modulus, 1.44 times 10 raised to X. So, multiply lang natin. We have FB 163.68. Now, ang lalabas ditong sagot is naka-Newton millimeter. So, divide natin yan ng 10 raised to 6. Sorry. 163.68 times your, ano ba to? SX 1.44 times 10 raised to 6. Times 10 times 6. So, 1.44. Sorry, nawala. 1.44 times 10 raised to 6. Makakancel lang yung 10 raised to 6, so hindi ko na siya lalagay. Diba may 10 raised to 6 dito, meron din sa baba. Alisin ko na tuloy. Mas madali. Equal natin. So yung lalabas dito is naka kilonewton meter. So yung sagot natin or the final answer will be the moment is equal to 235.7 kilonewton meter. So this is your answer for letter A. Ulitin ko, no, since ito kasi megapascal, tapos itong SX natin is mm cube. So ang lalabas dyan is Newton millimeter. So to convert that into kilonewton meter, we need to divide it by 10 raised to 6. Now since 10 raised to 6 sa numerator, 10 raised to 6 sa denominator, kinansel na lang natin kaya wala na siya. So multiplying these two will give us 235.7 kilonewton meter. Okay, so this is for your letter A. Ang B naman, what if your Fy is equal to 345? So ang gawin natin, copy na lang natin ito. Palitan nyo lang ng 345. $183.93. So if you'll notice, this is now bigger than your 170. So check din natin to. Palitan nyo lang ng 345. So 577, na-satisfy niya pa rin. Pero this falls under semi-compact, di ba? It is greater than 170 but less than 250. So we can say that the section is semi-compact. Now for your FB, yung medyo mahaba-haba yung equation, let's see. We have Fy multiplied by 0.79. So, unahin natin. We have 0.79 minus 0.00076 multiplied by, we have BF. Ang BF natin is 305 all over 2 times your TF. Ang TF natin is 15.4. Then multiplied by square root of Fy, which is 345. This will give us 0.65. Now, if you notice, hindi pa siya, na multiply pa natin yan sa FY. So, ang FB natin is equal to ang FB natin is equal to FY 345 multiplied by 0.65. So, ang FB natin is 224.45. So, ito na yung FB natin. Ang gagamit, so, FB times FY times ito. So, kinumpute ko muna yung nasa loob nitong bracket, which is 0.65 multiplied by your FY. This will give you your FB. Tapos, gayahin lang ulit natin itong ginawa natin kanina. Multiply the bending stress to your SX to get your moment. So, copy natin to. Palitan lang natin yung bending stress ng 224.25. Ayan, so the moment capacity of if your Fy is 345 megapascal is 322.92 kilonewton meter. So if you'll notice, the bigger the yield stress, the bigger the moment capacity. Okay, so ganun yung pag-compute kapag ang section natin is laterally supported. Now, in this case kasi, yung example natin is nakalagay na mismo yung nakalagay na laterally supported daw siya. But if, for example, hindi nakalagay na laterally supported, you need to compute for your LCLU. Kung papansin nyo sa example na to, obviously na hindi natin yan magagamit kasi wala naman na length na given. So, laterally supported yung ginamit natin na equations. Yeah. So, that is how you compute for a laterally supported section. Next, so next we have laterally unsupported beams. So, for laterally unsupported beams, we also have this condition. So, ito yung magiging basis natin. So, ito yung gagamitin natin na basis. So, you need to compute for this. Tapos, ang i-compute natin generally is this one, or your L over RT, or your limiting slenderness ratio. This was introduced sa columns, diba? But ang difference is, ipapapansin nyo merong subscript na T, yung radius of gyration. So, hindi to yung regular na R is equal to square root of I over A. This is RT is equal to square root of IT over AT. Iba yung R na kino-consider natin kapag bending. Hindi siya yung para sa entire section. So, i-define naman yun mamaya. So, yun. Please, wag interchange. Kapag bending, L over RT, do not forget the subscript. Now, if this is the condition na masasatisfy, we will use these two equations. Kung mapapansin nyo, dalawa yung equation na gagamitin kapag condition A. So, dito sa dalawang equation, ang gagamitin natin is yung greater value but it shall not exceed 0.6 Fy. So, ang gagawin pala natin is mag-compute tayo ng tatlo. Ito, and then 0.6 Fy. If the answer of these two is not greater than 0.6 Fy, pipiliin natin yung mas malaki. But if these two is greater than 0.6 Fy, we will use 0.6 Fy. Ulitin ko, no? In solving for your FB, we will compute three values. For this one, and for the 0.6 Fy. Now, these two should not exceed 0.6 Fy. If ever they do, we will use the 0.6 Fy. Pero ulitin ko, yung mas malaki sa dalawa, if they are both less than 0.6 Fy. So yun, this is the first condition, and then these are the equations. Yung L over RT, ito, i-copy nyo lang. Now, ang something nyo sa equation is yung CB. So, Fy is the yield stress, L over RT is the slenderness ratio. CB, meron din tong equation, Papakita ko mamaya. And then, take note nito ulit AF, no, baka area na naman yung lagay. This is the area of the compression flange. So, please be careful pa nagsusolve. Divided by your length times the depth of the entire section. Next, di ba, if L over RT is less than this and, greater than this equation and less than this equation, ito yung gagamitin. So, second condition is if mas malaki na yung L over RT dito. Kasi dito, di ba, less than siya. If greater than siya, ito naman yung gagamitin. Two equations again. If you will notice, same lang yung equation na 83 times 10 raised to 3. So, yung FB na to will both be used for these two equations. So, same lang siya. Ito lang yung magbabago. Ayan. So, ito naman yung equation kapag greater than yung L over RT sa square root of 3.520,000 CB over FY. So, yun. This is the first equation. Second equation, similarly, both should not be greater than 0.6 FY. Tapos whichever is greater should be used. Yan. Dalawa lang condition lang naman siya. Yung isa and ito. And then, for the equation of CB, we have this formula. 1.75 plus 1.05 M1 M2 plus 0.3 M1 over M2 squared less than or equal to 2.3. Now, yung M1, kapag nagbigay ng moment sa beam, yung M1 is the smaller, M2 is the larger. So, kahit saan sila nakalagay, yung smaller value ng moment should be the numerator. Yung larger is the denominator. So, M1 over M2 is positive when the moments are of the same sign or bending in a double curvature. M1 over M2 is negative kapag opposite naman yung sign and bending in a single curvature. Ano bang ibig sabihin? So, try natin i-drawing. Ito yung beam. Lagay tayo ng moment. Kunyari, ito yung moment. Ganyan. Kunyari, yan yung moment. Di ba kapag ganyan, this is same sign, di ba? This is positive. Kasi same sign, tapos double curvature na tinatawag. So, positive yan. So, kapag ang moment nyo naman is opposite sign, di ba, remember yung sign convention natin, smiley face, positive. So, this is positive. Kapag ang moment naman na binigay is in a single curvature or opposite yung sign, positive yung isa negative. Ganito. Same yung direction. This is negative sign. Please not interchange. Ganito yung sign convention. Na. So, positive, negative naman yung second figure. Next. CB is equal to 1 for simple and cantilever beam. So, if wala namang moment na naka-indicate sa problem, simple beam lang siya or cantilever beam, your CB will just be equal to 1. You don't need to use this equation. Now, if you'll notice, this should be less than or equal to 2.3. Now, if in case mas malaki yung CB natin sa 2.3, we will use 2.3. Okay, so, may mga conditions tayong ganyan lagi na. So, if simply supported or cantilever beam without a moment naman na given dun sa problem, we will just use 1. And then, the answer of CB, if in case na may moment, should not be greater than 2.3. And then, to determine your radius of gyration, RT, ang definition kasi ng RT, it is the radius of gyration of the area of the compression flange plus 1/3 of the area of the compression web. So, ganitong itsura. Area ng compression flange, ang compression flange kasi natin is yung nasa top, di ba? Kasi siya lang naman yung nagre-receive ng load, di ba? Kung may load tayo sa beam, andito yun sa top. Yung nasa ibabaw, this will be considered as your compression flange. Plus 1/3 of the area of the compression web. So, since ang compression web natin is in ito, so kung 1/3 pa, tapos divided by 2, kaya kung papansin nyo, naging over 6 yung equation dito. So, 1/3 nitong kalahati Kaya kung papansin nyo, this is D minus 2TF over 6. Bakit ganito? Kasi yung total depth, subtract mo, total depth, subtract mo yung TF. Dalawang TF, ang lalabas na resulta is ito. Tama? Total depth minus dalawang TF, ito yung lalabas. Divided by 2 para maging compression flange, compression web part. Divided by 3 kasi 1/3. Kaya ito yung equations na lalabas. So, to get the area nito and area nito. So, pwedeng gamitin nyo yung equation na to, but I highly suggest na para mabawasan yung equation na i-memorize nyo, i-drawing nyo na lang yung I-beam, tapos gawan nyo na lang ng label. I mean, di ba, madali lang naman makompute kung ano yung height na to. So, subtract mo lang yung, kukunin mo lang yung height ng web, tapos divide mo sa 6, makukuha mo yung height na to. And then, compute mo lang yung area. So, I suggest na wag nyo nang i-memorize to. Kasi mas mahaba. Tapos, for the moment of inertia, bakit natin kailangan ng moment of inertia? Because the equation for RT is square root of I over A. So, we need to get the moment of inertia. So, ang axis ng plane ng web natin is y-axis. Kung y-axis, di ba, ang magiging, kung magbi-BH cube over 12 tayo, ito yung base, ito yung height. Kaya kung mapapansin nyo, TF, base times height cube, which is your BF over 12, plus ito naman, BH over cube nitong 1/3 ng compression flange. So if you'll notice, baka medyo dagdag do sa equation na i-memorize. So I highly suggest, i-drawing nyo na lang yung I-beam or yung W section. Tapos, i-highlight nyo yung compression flange plus 1/3. Tapos, dito na lang kayo mag-compute ng area tsaka moment of inertia. So, yun. Then this is for your RT. So, kompleto na may CB, may RT. Yeah. RT is equal to square root of IT over 8. So, yun, let's have an example. Simply supported beam having a span of 12 meters carries a concentrated load P acting on the plane of the web. The beam is a wide flange section, W14 by 90. The properties are, so if the member is restrained against lateral buckling only, at the supports, find the maximum P that it can carry at its midspan. So yun. So here, hindi naman siya sinabing laterally supported, no? So first, ang gagawin natin is i-compute natin yung LC tsaka LU. Ayan. LC, 200 BF over square root of FY, less than L. LU, 138,000 AF. Ulitin ko, AF is area ng compression flange, so isang area lang. Yung top flange lang, kaya BF times TF lang to. Divided by the depth times FY. So both are less than your L. Yun, kasi ang length natin is 12 meters. Anong next step? Diba, ang magiging basis natin pag-compute is your L over RT. So next step is compute first for your RT. Now, how do we do that? Diba, square root of IT over AT. Now, if you don't want to use the equation, diba, sabi ko, i-drawing nyo na lang. Now, in case na memorize nyo yung equation, substitute nyo lang yung values. BFTF, D minus 2TF over 6 times CW. So, substitute nyo yung equations to get your AT and IT. Now, just in case naman na, kunyari, drinon nyo na lang yung I-beam, no? I don't require you to write this down. Kahit isulat nyo na lang, AT is equal to, kunyari sa solution, sulat nyo na lang AT is equal to the answer, IT is equal to this one, and then RT is equal to kung ano yung sagot. So, para masyado kasi itong mahaba. So, yan. We get AT and IT, tapos RT is equal to square root of IT over AT. So, we get 101.97 millimeters. Naka-mm sila, no? So, dapat mm. Then, makakompute na natin yung L over RT kasi yung hahanapin. Kasi kailangan natin siyang i-compare, di ba? So, compute natin. So, your L over RT, 12,000 divided by 101.97 will give us 117.68. Tapos, after nyo makuha yung L over RT, para malaman natin kung anong FB yung gagamitin, we need to compute these two. So, ulit, ang L over RT natin, 117.68. So, this equation gives us 53.34. This equation is 119.14. So, yung L over RT natin is greater than this one, but less than this. So, this is condition number 1. So, nag-fall siya sa condition number 1. So, ang gagamitin nating equation sa FB is itong dalawa. Papansin niyo, tatlo yung kinumpute ko, no? This one, ito. Now, simply supported, walang moment na naka-indicate sa problem. So, yung CB, papansin nyo, 1 lang yung nakalagay. Then, yung mga datang sinubstitute natin is given naman sa problem. FY, 248. L over RT, na-compute na natin. CB is 1. CB, ito ulit, AF ha, hindi siya area ng section. So, yun, 368 times 18. Length, 12,000. Depth, 356. So, we have 3 values of FB. Now, kung mapapansin nyo, FB and these two FB are both less than 148.8. Diba? We need to choose the greater value. So, your FB is 128.94. So, use 128.94, yung mas malaki sa dalawa. So, yung sa beam, kapag ganitong very direct yung question and given naman lahat sa problem, procedural siya. So, step by step yung pag-solve. Huwag lang kayong mamamali pag-substitute sa equation. Yan. Okay. Ang tanong pala is moment. Moment ba tanong? Sorry. Kala ko bending. Check natin. Carries a concentrated load P. Remember, it's find the maximum P it can carry at its midspan. Okay. Yung P pala, ano daw yung load na kayang i-carry nung section. So, from this equation, ang gagamitin natin is 128.94. So, di ba sabi ko kanina, ang FB nyo, since ito yung given, ang FB natin, ang FB, di ba, is equal to MC over I. Now, from this equation, makukuha natin yung M. Now, from M, makukuha natin yung P. Paano? Di ba? Kapag simply supported beam lang naman yan. Tapos, meron 12 meters yung span. Tapos, ang tinatanong is yung P. Ano daw yung P? Now, if you want to memorize, you can memorize the equations for the moment and kapag constants lang. Kasi kung i-compute natin, kung P yan, this will be, palitan natin yung column. This will be P over 2, di ba? P over 2. Kung gusto niyo lang i-derive, kunyari nakalimutan yung equation. So, P over 2. Diba ganyan? P over 2. Tapos, kung i-compute na natin yung moment, this is L over 2. So, this is PL over 4. So, kapag pala simply supported beam with a concentrated load at the midspan, the equation for your moment is PL over 4. Now, you can find table siguro kahit sa internet ng iba't ibang equation. Kapag simply supported beam with a concentrated load at the midspan, ito yung equation. Kapag uniform load naman ang load niya, that this is WL squared over 8. So, you can find here iba't ibang equation para mas madali. At least memorize this. Now, in case naman na makalimutan nyo, madali lang naman. Shear and moment diagram lang kayo to get the values. Kaya, it is very important that you know how to draw your shear and moment diagram. Kasi, for example, combined loading yung binigay, you can't use these regular equations. It is better that you know how to draw your shear and moment diagram para makompute yung equation. Now, for example, hindi kayo marunong mag-compute ng shear and moment diagram, anong gagawin? mag-cut lang kayo sa segment. Kunyari, sa center yung tinatanong na P, di mag-cut kayo dyan. Pag nag-cut ka dyan, di ba, ganito yung lalabas. Tapos moment, ang moment dito is yung nakuha mong moment, tapos makuha mo yung value ng P. This is P over 2, di ba? Tapos ito yung L over 2. Sorry, ang gulo na. Ulitin ko. So, for example, nahihirapan kayo sa shear and moment diagram. P. Sorry. P. Tapos ito P over 2. Kunyari, nakalimutan nyo yung equation. Tapos, ang tinatanong, ano daw yung P sa midspan. So, di ba, ang ginagawa natin is nagka-cut tayo. Remember, magka-cut kayo. So, dapat, it is important na alam nyo yung natuto talaga sa theory kasi magiging application, part na lang siya ng design nyo. So, magka-cut kayo sa gitna. Tapos, pag i-draw natin yung FBD, di ba? Will look like this. Tapos, ayun na. P over 2. Diba? P over 2. As this is L over 2. This is your moment. Diba? So, your moment is equal to dito pa din, PL over 4. Yan pa rin siya. So, pwedeng huwag nyo na itong kunin. Direkta na yung moment na na-compute natin using your MC over I. Kunyari may value na tayo, meron tayong length, makukompute natin yung P. So, if you don't want to draw the shear moment diagram, you can cut any portion kung ano yung tinatanong na value. So, equate lang yung ginagawa natin. Check natin. Ayan. So, here, ito na yung FB, MC over I. Makukuha natin yung M. Yung FB ginamit natin is 128.94. So, the moment is 301.12. Now, here, I use the derived equation. Pero ulitin ko, no, just in case na makalimutan nyo, you may just cut the section kung saan hinahanap yung value ng P. I-equate lang naman natin. So here we have the value of P, 100.37. So yung beam na to, ang maximum concentrated load na kaya niyang i-carry at midspan is 100.37. So ito yung mga limit na binibigay sa sections. Kumbaga pag nag-exceed sa 100.37, magkakaroon na siya ng failure sa bending. So yan. Ulitin ko lang if ang magandang i-memorize nyo yung mga common equations ganito. Marami naman yun sa internet. But it is better that you know how to get this without by just doing the shear moment diagram or yung pag-cut lang natin sa sections ng beam. Yan. So, let's have this example. So, a concentrated load P is acting at the center of the beam, having a simple span of 9 meters. The beam is made up of void flange with yield strength of 345. The beam has lateral supports with spacing 3 meters. Neglect the weight of the beam. So yan, what is the maximum unbraced length of the beam to consider it as laterally supported beam? Determine the allowable bending stress using nscp specification. So, solve natin, no? So, dito, hindi natin, may lateral support siya sa spacing na 3 meters. Pero yung length ng beam natin is 9 meters. So, how does it work? Solve natin. Solve natin, no? So, a concentrated load P is acting at the center of the beam having a simple span of 9 meters. So, paano ba siya nag-work? Ano bang... kasi ang, kunyari, ito yung beam, no? Simple beam. Tapos, meron siyang support, lateral support at 3 meters. So, sabihin natin ganito, no? At 3 meters. So, ang magiging length ng beam natin, may lateral support kasi siya at 3 meters. Yan, tatlong. So, this is a laterally supported beam. Pero ang length ng beam natin, hindi 9 meters. That will be equal to 3 meters na lang. Sorry, 3. So, ang L natin is actually equal to 3 meters. No? Kasi laterally supported siya at this point. So, di ba, ang definition, dapat ang length ng unbraced beam or unsupported beam. So, yung 3 meters, ito yung, this is your unsupported length. No, take note na ito yung unsupported length natin or unbraced length na tinatawag. Kaya ito yung gagamitin natin. So, mas magandang basahin nyo muna yung problem no, before dire-diretso. Kasi, mostly sa mistakes, no, L is 9 meters, so L is equal to 9, tapos magsasolve na agad. So, mali na. So, you need to understand the problem first. So, yun, no? Ito kasi yung unbraced length or unsupported length na tinatawag. Brace natin. So, yun. Ang tanong is, what is the maximum unbraced length of the beam to consider it as a laterally supported beam? So, check natin. Compute muna natin yung LC tsaka LU. Ang LC natin, LC natin, di ba, 200 BF, 200. Didira-diretso ko na. 200 times your BF, 360. Divide ko muna. 200 BF times your BF. BF is 360 times square root divided by square root of Fy. Square root of, ang Fy natin is 345. Ito yung LC, di ba? Ito yung equation ng LC. So, your LC is divided by 1,000 para maging millimeters. So, this is 3,876.36 millimeters. No? So, sulat natin. So, your LC is equal to 3,876 mm. Next naman is your LU. Diba, ang LU natin is 1378. 378. Kulang pa siguro ng 0. Check natin. Wait lang. Hindi ko sure. Baka mamali ako. LC over LU. Check natin. Start. 138000. So, kulang ako ng isa. Times AF over DFY. Yan. 18000 times area of the flange. Di ba sabi ko area ng flange? Area BF times TF, 360 times TF is 80 over DFY. Depth is 350 times your FY 345. Tama ba? So, yung LU natin, is equal to 7,395 mm. So, ang question is, what is the maximum unbraced length of the beam to consider it as a laterally supported beam? So, ang tanong kasi is, ano daw yung maximum unbraced length ng beam para maging laterally supported? So, para maging, ang LC natin, di ba, ang rule is kapag greater than sa LC, magiging na siyang laterally unsupported. So, therefore, ang magiging maximum length para laterally supported is equal to, ito yung sagot, 3,876. Bakit? Kasi kapag nag-exceed tayo sa 3,876, magiging laterally unsupported na siya. Kaya naintindihan? Kasi ang length natin ngayon is 3 meters. So, laterally supported siya. Ang tanong, ano daw yung maximum length para laterally supported pa siya? So, ang maximum mo is 3876. Kasi nga, pag nag-exceed ka dito, that will be, that will be laterally unsupported. So, ang sagot sa letter number 1 is ito. Ito yung sagot natin. Ito yung maximum length para matawag natin na o makonsider natin as laterally supported yung beam. Okay, next. Determine the allowable bending stress using nscp specifications. Now, since we know that this is laterally supported, kasi nga yung L is less than LC, ang L natin is 3 meters, di ba? We will use now your BF over 2TF, square root of Fy. Yun na yung gagamitin natin. Copy ko na lang dito sa kabila para madali. BF 2TF, tama ito, BF 2TF times square root of F. Copy ko lang to. So, to solve, di ba? Kapag laterally supported, BF over 2TF, ang BF natin is 360. Ang 2TF, TF natin is 18. Ang Fy natin is 345, sakto. Yeah. Equals 185.742. So, this is greater than 170. Di ba? So, semi-compact to. Check din natin yung isang equation. Copy ko lang. Feeling ko semi-compact na eh, kasi mas malaki na siya. Copy ko na to. Okay, natin sa kabila. D over dtw. Ano ang depth natin? Depth is equal to 350. So, tulad nito, wide flange siya. Kung papansin nyo, mas malaki yung width niya dun sa depth. TW is 12. 345. 541. So this section is semi-compact. Now, kapag semi-compact, ang gagamitin natin equation is ito. Copy ko ulit. Semi-compact. Your FB is equal to this. Palitan lang natin ng 0.076 BF over 2TF. BF is 360. 2TF. TF is equal to 18 times square root of Fy. Check natin. So 0.649. So your FB is equal to, we have 0.649 times your Fy na 345. This will be your FB. So your FB is equal to 223.905 megapascal. So ang tanong lang naman, determine the allowable bending stress using nscp specifications. So ang tamang sagot is ito rin. Ito na yung sagot for letter B. Okay. So that is how you solve this problem. So, unang-unang tulad nito, check natin kung laterally supported ba or hindi para alam natin kung anong analysis yung gagawin. Sige. Problem number 2. Yan. Buka ulit tayo ng another. Problem number 2. A simple beam having a simple span of 8 meters is subjected to a moment M at the left end, counterclockwise, and 25% of M at the right end of counterclockwise. Clockwise saka counterclockwise. Tapos, it has no lateral support, and the section has the following properties. So, wait lang. Ano ba yun? Dito na lang natin isolve. So, copy ko yung problem, no? Pati yung ito. Find the maximum slenderness ratio, allowable bending stress, and then moment capacity. Natin. So, first step, drawing nyo muna yung beam. Kung anong itsura niya. So, ganito daw. Ito yung beam. Tapos, meron siyang subjected to a moment at the left end clockwise. So, ito clockwise siya. This is 0.25 m. Sorry, 25 m. Sa kabila naman, counterclockwise. So, ganito. So, this is m. Ay, mali. Left. M pala sa left. So, m sa left and 0.25 sa right. So, m. This is m. And then this is 0.25 m. Yeah, so it has no lateral support. Section has the following properties. So ang length natin is 8 meters. So length is equal to 8,000. So first step, compute natin yung LC, no? We have 200 BF over 2TF times square root of, nabaliktad ko. This is square root of Fy pala. Square root of Fy. So ang LC natin is, double check na lang, this is 2667. So length is greater than LC. Check naman natin yung LU. So 138 AF over DFY. Lalabas na sagot dyan is, substitute nyo na lang, no? Lalabas na sagot is 3505.30 millimeters. So, therefore, your L is greater than your L. So, therefore, this is laterally unsupported. Lateral unsupported siya. So, ang pag-solve, di ba, we need to solve for your square root of 7932 CB over FY. So, solve natin. To solve, ang equation natin is 700. Copy na lang natin para madali. C. So, nag-fall siya sa category nung laterally unsupported din, no? So, copy natin tong equation. Copy natin to. So, ito yung isa-solve natin. Now, before we can solve this, compute muna natin yung CB. Diba? Wala tayong value ng CB. Since merong moment, sorry, but meron ito nito. Then, since meron tayong moment sa, tawag dyan? Ito pala kasi. Ito yung beam. Since meron tayong moment, kailangan natin computein yung value ng CB, hindi lang siya 1. So to solve for that, we have your equation CB is equal to 1.75, diba? Plus 1.05 M1, M2. Then plus 0.3 M1, M2 squared. Now, since ang M1 natin dapat is smaller, so definitely ang M1 natin is 0.25, M2 natin is M. Now, makakancel lang naman yung moment dyan. So, pwedeng ang ilagay nyo is 0.25 na lang. So, CB, 1.75 plus 1.05. So, M1 is 0.25 divided by 1. So, 0.25 plus 0.3 25 squared. So, ang lalabas, check natin. Ang lalabas niya na sagot is CB will be equal to 1.51. Now, since this is not more than 2.3, di ba? May condition tayo, this should be less than or equal to 2.3. Now, since less than naman siya, we will use this as your CV. So, ang gagawin natin is substitute natin yung values. Substitute natin yung values dito. Wala pa pala tayong L over RT. Sorry. L over RT. Balikan natin yung equation. Kung mapapansin nyo dito sa given na yung RT, so you don't need to compute for your square root of I over A. There are cases, and most of the time, given talaga yung value ng RT nyo. So you don't need to compute yung moment of inertia saka area dun sa compression flange plus 1/3 nung compression web. So, since given na siya, madali lang yung pag-compute ng L over RT. Compute lang natin. L over RT is equal to 8,000. So, tapos lagay nyo na lang yung RT kasi binigay na siya, which is equal to 53. Then, the common error, no, kahit binigay na yung RT, kino-compute pa. If naka-indicate naman, hindi siya R ang nakalagay, RT, please use that instead of computing para hindi na mahaba yung pag-compute. So, ang magiging L over RT natin is 50.94. Meron na tayo L over RT. So, ito na magiging basis. Sorry. Check na muna natin yung ito. Substitute natin yung CB, which is 1.51. Tapos, divided by FY, which is equal to 248. Ang lalabas dyan na sagot is tingnan natin. 65.44. Ang L over RT natin, ano nga? Sorry. 150.94. So, 150.94. So, greater than siya. Check na lang natin itong isa kung greater than ba. Ang lalabas is 3520 square root CB 1.51 over FY. Sorry, ang lalabas is 146.32. So, greater than siya. Greater than, no? So, this is case 2 ang gagamitin natin na equation. Hindi yung isa, so yung pangalawa, ang pangalawang equation, lagay natin. So, this is case 2, mas greater siya sa L over RT. So, ito yung dalawang equation na gagamitin. Copy natin. Ito yung gagamitin, dalawa yan. Copy natin. Mas madali. Yeah. Yun lang naman yung kailangan yung gawin, no, para malaman nyo kung ano yung bending stress na gagamitin. So, yun. Ito yung gagamitin nating bending stress. So solving, CB, ito na 1.51, L over RT, ito na 150.94. Ito na punta dito. So yun, so yung L over RT natin, makukompute na natin yung FB. Computing now. Compute natin. So magiging FB is equal to, ang FB natin is equal to, ito is, this is 77.68. Ito namang isa. Ulitin ko yung AF na to. This is, itong AF na to, area ng flange yan ha. Huwag mong gamitin yung area yung binigay. CB 151. So we have 98.45. Now, ang 0.6 FY, ito, check natin, tatlo pala yan. FB is 0.60. Ang FY natin is 248, tama? 248. It's 148.8. Again, use the bigger value, but not greater than 148. So, ito yung gagamitin natin, FB. So, we now have FB is equal to 98.45 megapascal. Now, yan yung unang tanong. Determine the maximum slenderness ratio. Maximum slenderness ratio, sorry. Dito sa tatlo, ang maximum is 150.94. Kasi siya yung pinakamalaki. So, ito yung sagot. Next naman, what is the allowable bending stress? Ito din yung sagot. Next, what is the moment capacity? So, balik tayo sa equation na FB. Anong binigay? SX ba o I? Check natin. Ang binigay po ay SX 2.06 times 10 raised to 6. So, yun ang gamitin natin. So, M. Ang moment natin equal to FB 98.45 multiplied by SX. Sorry, nakalimutan ko agad. Ano na yun? 2.06 times 10 raised to 6. 2.06 times 10 raised to 6. Divide natin ng 10 raised to 6 para maging kilonewton meter. Yung lalabas na moment capacity is 202.81 kilonewton meter. So this is the answer for letter C.